Welcome back. Okay, in this video lesson we're going to talk about how you can use SD to check for inconsistency. So remember when we had when we were talking about consistency when we were doing semantics, what you had to do was see whether or not there was a truth value assignment on which all the sentences of a set can be true. Now, we can't actually check for consistency in SD. What we can check for is inconsistency. And it should hopefully be clear why you actually can't check for consistency in SD. But we can check for inconsistency. So what does it mean for a set to be inconsistent? Well, in the semantic notion, like we just said, it means that there's no truth value assignment where all the sentences can be true. What this basically means in SD is that you can derive a contradiction. So if a set is inconsistent, then you can derive a contradiction, which I just abbreviate as this here. So this means contradiction. So if we want to see whether or not a set is inconsistent, we can use SD by deriving a contradiction from assuming each of the members of the set as primary assumptions. So let's go over an example, and this example comes from this will be 5C. That's right, in the current homework assignment. Okay, so here's what we want to claim. We want to claim that the following set, A if and only if B, if B, then not A, and A. We claim that this set is inconsistent. So what I need to do is derive a contradiction from assuming each of these is my primary assumptions. So the first thing I do is I draw my main scope line, and oh, I didn't mean to do that. So I will assume A if and only if B. My next primary assumption will be the next member of this set, which is if B then not A. And just so you know, I mean, this might look confusing at first, but you have to keep in mind that although these sentences just have one main connective, you might have a complex sentence in here that has several different connectives in it. And the way you can tell where the sentences end are by the actual commas. So whenever you have a comma, that separates this sentence from the next sentence that might actually appear. So it's important to make sure that when you're building up your derivation, that each of the members of the set, namely each sentence, which could be the complex sentence, is its own primary assumption. Okay, and then we also have one more, which is A. So these are our primary assumptions, and what we need to do now is derive some kind of contradiction, right? So we need to get some case where we have, not Q and Q. That's our goal, to show that this set is inconsistent. And as in a lot of the cases with negation introduction and negation elimination, the goal there was to get a contradiction in a subderivation. And that required us to look at where the negations are in primary assumptions. And hopefully you try to find atomic sentences that have negations in front of them, but every once in a while you might not be able to do that. You'll need to look for a complex sentence that has a negation in front of it. But in this case we're lucky, so we have not A here and we have A here. So it looks like a good candidate for getting ourselves a contradiction is going to be A and not A. So we're going to make this our goal, right? In the one case we want to get not A, and in the other case we want to get A. And this A, this will be really simple, right? I mean, this we'll just be able to get by reiterating from line 3 up there. So what we want is to get not A. So how do we do that? Well, when we have a negation, a good strategy we had was to use negation elimination. And negation elimination requires that we find a contradiction. Now that would actually be an okay strategy to use to actually be able to get not A. But since we have to find a contradiction inside that subderivation anyways, we should try to see whether or not we can get a contradiction right out here in the main scope line, which will be a little bit shorter. So, so let's do that. So we have A, and we notice that what we want to get, not A, is here, the consequent of a conditional. And we notice that the antecedent of that conditional appears in another sentence of the primary assumption, namely up here. And our goal then is to try to get B out from this biconditional. And so we need to look to see what the other component is, which is A, and we actually have that. So now we have this sort of chain of reasoning that we've done informally of how we could get out not A, by first trying to get B, and then the way we can get B is from over here, and then in order to get B from over here, we need to get A, and we're actually already given that. So using that kind of backwards reasoning, we can actually then unfold what that derivation is like. But if you want to see sort of what we have in mind when we're sort of building up backwards, is we're going to get not A by doing the conditional elimination from line 2, and we don't yet know where, but we're eventually going to get B. So we're going to write down B here because we're going to use B and 2 to get not A. And so where can we get B from? Well, we want to get it from here, this biconditional. So we're going to do biconditional elimination on line 1. Oh, sorry. That should be biconditional elimination on line 1 and some other line above it where we had A first. And then it becomes immediately clear that we're actually already done the derivation because we're already given A. So in fact, we don't even need to write A down here. We could actually just use line 3 to cite our derivation. So I can actually scratch this out. I could have put reiteration here if I liked, but that would take us a little longer than, it would give us a proof that's a little bit longer than necessary. So I can actually now write down 3 here, right? Because using A and A if and only if B, I can do conditional elimination. So that's line 4. And then I can use, I can now fill in this justification for lines 2 and 4 because we use that to get us the not A. So this will actually be conditional, oh sorry, I already have that, conditional elimination on line 2 and 4. And then we can just reiterate here for A. So this turns out to actually be relatively short. This is actually only 3 steps. But there's another way we could have equally done this as well. And if you want to see what that would look like, this would be a little bit longer, but this would be just as good. Is suppose we didn't yet actually do this. Suppose we went a longer route, and what we did was first assume A to then actually try to get a contradiction. And hopefully you'll see that the strategy that we just used out here in the main scope line would just sort of apply in here, right? Because since we're assuming A, that means we can get B by biconditional elimination on, on line 1 and 4. And since we have B, that would allow us to actually get not A. Oh, sorry, not A, from line 2. And this would be conditional elimination from line 2 and 5. And then we already have our contradiction, right? We can use reiteration here if we liked. From line 4. And then we would be able to pull out not A, and this would give us line 8. And we'd have to change these numbers accordingly. So that's just another way we could have done this as well, but notice that this is a couple extra lines long. And the goal in general is to try to keep your derivations as short as possible. Okay, let's do one more actually. So we've shown that this set is inconsistent. Let's do another problem. Let me switch colors here. Okay. So let's do, this problem is from 10C. And what we want to show is the following set is inconsistent. C if and only if A, that's the first member of our set, and the second member of our set is C if and only if not A. And actually, for what it's worth, I think they have this swapped. I think this comes as the second member of the set, but sets don't actually order. Sorry, sets are not ordered. In other words, you'd have the same set if this was over here and if this sentence was over there. It would be the exact same set. Okay, so we want to show that this is inconsistent. So what we need to do is try to get a contradiction. And it should be pretty immediate where we're probably going to get this contradiction from, between not A and A. So our goal then is to get A and not A out on our main scope line, and our primary assumptions are going to be C if and only if A, and our second assumption is going to be C if and only if not A. Okay, so this is a little bit trickier, right? We don't have another sentence letter like C so that we can just use biconditional elimination to take out A. So this is going to be a little bit trickier. So one of the things we now have to do is try to use the strategy that we did before by doing the negation elimination or the negation introduction. So to get not A, one of our strategies will be to assume A and then to try to get a contradiction. And then if we do that, then we can use negation introduction, citing this whole subderivation. So that's a strategy to get not A. And we're going to use a similar strategy to get A as well. And I'm just going to rewrite this up here. And then you can just imagine that this is actually just by reiteration, if you like, from this line up here. So in this case, we're going to try to assume not A and try to get a contradiction so that we can do negation elimination. Okay, so how do we do this? Well, let's start with this subderivation here, since this is the one we wrote down first. So we want to get a contradiction somewhere in here, and we notice that we could actually that not A contradicts with our assumption A here, and we also notice that, well, C actually kind of connects. C is common to both of these primary assumptions, right? If you had A, then you could get C, and then if you get C, you could get not A, and vice versa. So it's this sort of reasoning that we're going to make use of here. So since we have A, then we can use biconditional elimination to actually be able to get C. Right? We can use biconditional elimination. And we need to put in the numbers here, but we'll do that when we actually finish this top part of the proof first and next. Okay, so now that we have C, now we can actually get not A by, again, doing biconditional elimination. And again, we'll have to cite those lines. And not A actually contradicts with our assumption A. And this is exactly, and so I could use reiteration here. This is getting a little, there we go, a little tight. So now we have not A, and that's all I needed to be able to introduce the negation symbol, not A here. So we need to then also get A, and we're going to use a similar strategy that we just did, and I'm probably going to sort of run out of room. So let me actually just blow this up a little bit. So we'll pretend that this is not A. Oops. That's terrible. Let me fix that real quick. Okay, so we have not A. And we're going to use a similar strategy. So we have here, we can get C out by doing biconditional elimination on line 2, and this is going to be line 3, right? So this is lines 2 and 3. And then since we've got C, then we can actually get A out. Again, by biconditional elimination. And this time we'll use lines 4 and 1. And this is line 5. And then I'm not going to do it here, but you can reiterate not A to show that we actually have the contradiction. Actually, maybe it's worth doing just to make sure we're clear. So this will be by reiteration from line 3, and so this will be line 6. Okay, so this is just me blowing up the subderivation right here. So this will actually be line 7 now. And we can use this negation elimination, right, because we assumed not A, and we showed that we could get a contradiction from it. So this is going to be from lines 3 through 6. Sorry for the mess. 3 through 6. This is sometimes what happens when you do the rough work. And then you sort of rewrite everything so it's a little bit neater. But in any case, let's finish up here. So this is going to be line 8, and we're making this assumption. I guess I skipped these as well. I'm being a little bit lazy here. I don't mind if you guys don't write it down. It's actually more of a heuristic for yourselves to help you. So I won't be too sort of harsh about this, but it is a good idea, at least at the beginning, as you're still getting comfortable with derivations, to sort of write this down. So I'm making this assumption here for the purposes of negation introduction. And I probably should have written this up here too. I'm making this assumption for the purposes of negation elimination. Okay, and then what I need to do here is I use biconditional elimination, remember, on lines 1 and 8. So this is line 1 and 8. I promise you that's an 8. Then we got not A again by biconditional elimination on line 9 and 2. So this is lines 9 and 2. This we got by reiterating from 8. We got not A from doing negation introduction from lines 8 through 11. And then we just did A again by reiterating it from line 7. And actually, this is a good point. I could not do reiteration from line 8. Remember, because we've closed this subderivation, so I can't actually go back and access anything in there. I can only access the things that are still open, and this has been closed off. So I can't actually go back and get A from 8. I have to get it from 7 here, which is still open. Okay, so now we have the contradiction that we need to claim that this set is inconsistent.